Good day everyone! I'm Leslie May Bognot and I'll be presenting to you the infographic about the hidden patterns our group found from the Pascals Triangle. Pascal's Triangle is a number triangle which, although very easy to construct, has many interesting patterns and useful properties. It was named after the French mathematician Blaise Pascal, who was born in 1623 and died in 1662, who studied and published work on it. The triangle's construction is very simple. Start with the one at the top. Each number below this is formed by adding together the two numbers diagonally above it, treating empty space on the edges as 0. Therefore, the second row is 0 plus 1 equals 1 and 1 plus 0 equals 1. The third row is 0 plus 1 equals 1, 1 plus 1 equals 2, 1 plus 0 equals 1, and so on. So this is Pascal's triangle with 9 rows, but it can be extended infinitely by repeating the addition process. Pattern number 1. We have the powers of 11 pattern. The numbers in each row form the digits of every nth power of 11, starting with n equals 0 at the top row. So for the first row, we have 11 raised to 0 equals 1. Then 11 raised to 1 equals 11. Next is 11 squared equals 121. Then 11 cubed equals 1331. And 11 raised to 4 equals 14,641, and so on. Pattern number 2. If we cut the triangle in the middle, the numbers on the left side have identical matching numbers on the right side. Therefore, the total sum on the right side is also the sum on the left side. Again, the triangle is symmetrical. The numbers on the left side are also found on the right side of the triangle. Pattern number 3. The binomial expansion pattern. Binomial is a term that is used to add two things together. It refers to the pattern of coefficients, which are the number before the variables. When we multiply the binomial by itself certain number of times, we get the coefficients. It is written as quantity a plus b times n. Example is quantity a plus b squared, which is equal to a squared plus 2ab plus b squared. In this polynomial, the coefficients are 1, 2, 1. The coefficients of the succeeding expanded binomials will be found in the next rows of the Pascal's triangle, as shown below. Pattern number 4. The geometric sequence pattern. The sum of the numbers in each row has a common ratio of 2, and therefore it forms a geometric sequence. Pattern number 5. We have the powers of 2 pattern. If we look at the numbers of individual rows of the triangle, the sums are doubled for every row. The sum of each row is equal to 2 raised to n. We can observe that the sum of the numbers in each row is equal to 2 raised to n, where n is equal to the number of rows, starting from 0, 1, 2, 3, 4, 5, 6, and so on. Pattern number 6. The patterns in diagonals. Each diagonal in the triangle has different sets of numbers. First are the ones, followed by counting numbers, triangular numbers, tetrahedral numbers, pentatope numbers, and 5 simplex numbers. And lastly, pattern number 7. Arrange the triangle in different way, and you can see Fibonacci sequence pattern. Look at the parallel lines drawn with each cut through several numbers. Let's add together the numbers on each line. First line we have 1, second line we have 1, third line is 1 plus 1 equals 2, fourth line is 1 plus 2 equals 3, fifth line is 1 plus 3 plus 1 equals 5, and sixth line is 1 plus 4 plus 3 equals 8, and so on. By adding together the numbers on each line, we get the sequence 1, 1, 2, 3, 5, 8, 13, 21, and so on, otherwise known as the Fibonacci sequence, a sequence defined by adding the previous two numbers together to get the next number in the sequence. So that's all for our group. Good day and God bless. Thanks for listening.